All right, folks, so section 5.1 today. I'm really hoping this is the last video lesson, cross my fingers, that we'll be putting together all year. But section 5.1. So just as I've warned you before, we're going to be relying on the skills that we learned in chapter 4 as we work through this lesson in chapter 5. We'll start off with a bit of a warm-up problem. You should be able to handle this problem from your work done in section 4.7. So we're handling something like this. If you have an idea, by all means, pause the video, go for it, and then unpause and fast forward a little bit and double check your work. But if not, we'll go through this here. So here, I need to evaluate this entire expression. And if I'm going to do that, I need to respect my bed mass. I need to evaluate the inside of these brackets first. And if I'm evaluating these, to evaluate the inside of my brackets, I need to evaluate these individual trig ratios. So I have the sine of 30 degrees. That's nice and extremely straightforward. The sine of 30 degrees, well, if I'm evaluating something like that, I'll need my special triangle. I know how to evaluate something like this. Do something here. All right, side length 2, side length 1, side length the square root of 3. My angle up here is 30 degrees. My angle down here is 60 degrees with a right angle there. My sine of 30 degrees, there's my 30 degrees. I know that the sine of 30 degrees is going to be equal to my opposite side over my hypotenuse from my 30-degree angle, and that means I'm working with 1 over 2. Fantastic, nice and straightforward. We're already making progress evaluating this expression right here. So that means that the inverse tangent of not the sine of 30 degrees, I can now substitute in what I just found of 1 over 2 minus the cosine of 240 degrees. Well, hang on. I don't have a special triangle with 240 degrees, but what I do know is that I can take advantage of my cast rule, just as we learned in the previous chapter. I can take advantage of my cast rule way over here, and I can say, okay, 240 degrees, that's more than 90 degrees. It's more than 180 degrees, but it's less than 270 degrees. So I'm looking at something like this. So according to my cast rule, CAST, according to my cast rule, my cosine function is negative down here. It's negative up here, positive, and positive. And if that's the case, then that means that my cosine of 240 degrees is going to be equal to negative the cosine of the related acute angle. Well, hang on. What is my related acute angle right here? My related acute angle is going to be equal to 240 degrees. That's what I started with. 240 degrees, that's all the way around, minus this part, the 180 degrees. So 240 degrees minus 180 degrees. I suspect I could have written this in another spot to give us more space, but that's okay. Minus 180 degrees. I'm working with a related acute angle of 60 degrees. So that means the cosine of 240 degrees is equal to negative the cosine of 60 degrees. If you're unsure on this, again, section 4.7. So, all right, negative the cosine of 60 degrees. Well, let's input that information way up here. I'm working with negative the cosine of 60 degrees. And then I can simplify that a little bit further. That is the inverse tangent of 1 over 2 minus, really it's plus, the cosine of 60 degrees. How can I evaluate the cosine of 60 degrees? I know how to do that. I can evaluate the cosine of 60 degrees using the exact same special triangle that I've already sketched. This time I'm working over here, and I'm working with the cosine. So the cosine of 60 degrees, I know is going to be my adjacent side to 60 degrees divided by my hypotenuse. Fantastic. My adjacent side is 1, my hypotenuse is 2. This trig ratio is equal to 1 over 2 as well. So I'm working over here. I can simplify this okay. So I'm working with the inverse tangent of 1 over 2 plus 1 over 2. Easy. Nice work, folks. So I'm working with the inverse tangent of 1. And really what this means is I'm working with whatever angle brings me the tangent ratio of 1. So that means, if you'll bear with me here, that means I'm working with whatever angle, the tangent of theta is equal to 1. What angle gets us that? Well, if we're going to double check that, we'll need, again, a special triangle. This time, our special triangle, let's go with pink again. I like that color for our special triangles. We're working over here. We have side length 1, side length 1, side length the square root of 2. I have 45 degrees in here. I have 45 degrees in there. And I learn that, okay, 45 degrees, if I'm taking the tangent of 45 degrees, I can see I'm working with my opposite side over my adjacent side. I'm working with 1 over 1. That's equal to 1. That's what I'm looking for. So that tells me that my theta is equal to 45 degrees. Now, we solved this entire problem. Was it complicated? Yes. Did we use a lot of the skills we learned in the past chapter? Absolutely. But what's key here is that we only used the skills that we learned in the past chapter to solve this problem, to solve that theta is equal to 45 degrees. Fantastic. Now what you should be able to do is evaluate the next one, the tangent of 225 degrees. You should be able to evaluate this nice and straightforward using those same skills, some of which we've already demonstrated in the first part of the warm-up. So try that out. I'll encourage you to pause the video, try it out, and unpause it when you are done. Good, so our solutions should look something like this. We can use our cast rule to write the tangent of 225 degrees in terms of its related acute angle. And then we can evaluate the tangent. This time we're working with 45 degrees once more, and we find that the tangent of 45 degrees is equal to 1. So my question for you is, what do you notice? From both of these warm-up problems here, what do we notice? Well, I'm hoping you can put together that in the first warm-up problem, we were looking for a theta where the tangent of that theta equaled 1. And our conclusion was that theta had to be equal to 45 degrees. But then we just found out that the tangent of a different angle equals 1. The tangent this time of 225 degrees. So we need a strategy to be able to find both of these solutions. We need to be able to find all solutions when we're simplifying a problem, not just one solution that theta equals 45 degrees, because this is an incomplete solution to the warm-up problem. If it was a complete solution, it would have included the solution theta is equal to 225 as well. Theta could be either equal to 45 degrees or 225 degrees. So we'll work forward. You could write that using your own words right here. I left a little bit more space. Obviously, honestly, you could say it in one sentence or so, but I wanted all of this to be on one page. So I brought it down here. Now, and we'll keep going here. Whoops, Sadie the puppy is doing her best to try and keep her volume down, but she finds it distracting when she hears other callers walking outside. So I'll do my, whoops. And actually she's been sent on her way because she couldn't keep quiet. That's okay. So we're working in here. We're going to rely on a few different pieces here. Number one, we're remembering that xy is equal to the cosine of theta and the sine of theta, not times. Those are the coordinates. Now, if this is true if we're working with a unit circle, we'll be using that later on. Now, if we're going to solve a problem, remember, often on assessments, all the instructions you get are to solve. That's it. That's all it'll say. And you need to remember what that means is that you're trying to find the values for the unknowns, whether you're working with x or you're working with theta. You need to find the values of the unknowns that make this statement, that make the equation true. So the strategy that we're going to use here, we're going to, and you might want to pause the video, fill in your own blanks. We're going to rearrange so that our trigonometric ratio is isolated. So let's try something like this. What is our trig ratio here? Our trig ratio is the sine of theta. Is that isolated? Yes, it's already isolated. Good job, us. We've already completed the first step. All right, next we want to draw a special triangle with the required ratio. So that means we want to draw a special triangle so that we have root 3 over 2. Well, hang on. Where do we want these root 3's over 2? Well, we know the sine of theta is equal to my opposite side over my hypotenuse. So I'm looking to have a special triangle, in particular with a hypotenuse, the square root of 3. Square root of, with a hypotenuse of 2. That makes a lot more sense. Okay, do I know a special triangle like this? Absolutely. 2, 1, the square root of 3. I have a 30-degree angle on the top. I have a 60-degree angle on the right side and a right angle right here. Good. That's step 2. Next, what we're going to do is find the related acute angle. This is the step that differs from our approach in the warm-up question. And if you're not sure, head back up there and double check, compare our strategies after you know what you know here. So we need to find the related acute angle. If we're finding the related acute angle, all we need to do is to find which angle has an opposite side of root 3 and a hypotenuse of 2. And the key here to remember, what we're solving for is not theta. What we're solving for is alpha. All right, so if I'm looking in here, I see that 30 degrees, nope, that 60 degrees down here has an opposite side of root 3, has a hypotenuse of 2. That's what I'm looking for. So our conclusion is that alpha is equal to 60 degrees. Good job. Next, we need to use our cast rule. So we want to use our cast rule to determine where our theta, remember, which is different than alpha, where our theta lies. So we'll jump in with our cast rule. We should be masters of sketching this right now, C, A, S, and T. And we know that we're working with here a sine ratio. So our sine ratios, I know that sine is positive in quadrant 2. I know it's positive in quadrant 1 because all of the ratios are positive in quadrant 1. But only tan is positive in quadrant 3, so it's a negative here. And only cosine is positive in quadrant 4, so again, it's negative there. So that means the ratio that I'm working with right here is positive. And if it's positive, that means that I must be working in either quadrant 1 or quadrant 2. I know that I am not, under no circumstances in this problem, and am I working in quadrant 3 or quadrant 4. Good, so I've used that logic, I've used my cast rule. Now I need to evaluate my theta. And I can evaluate my theta by using my related acute angle, which is shared in here, right? So my related acute angle, and you know what, I'll sketch it in that light blue that we used to find it. My related acute angle, if I'm working in quadrant 2, shows up here. My related acute angle, if I'm working in quadrant 1, shows up right here. So since I have two terminal arms, then I'm expecting to have two potential solutions. So my theta 1, which we'll say is in quadrant 1, theta 1 looks like that. My theta 1 is actually just equal to my related acute angle. So theta 1 is equal to 60 degrees. That's one of my solutions. But there's another terminal arm, so I need to head around here. This is theta 2. How can I find theta 2? Well, I need to come up with a statement. So I know here that 180 degrees is going to be equal to my theta 2. If I go around in the circle in a counterclockwise fashion, my theta 2 plus my related acute angle right in here. Good. Luckily, I know my related acute angle is 60 degrees, so that's theta 2 plus 60 degrees is equal to 180 degrees. I subtract 60 degrees from both sides, and I find that theta 2 is equal to 180 degrees. I'm just going to move this over to give ourselves enough space to solve the next problem. Good. So where I'm working right here, I just found two solutions. So therefore, theta is equal to 60 degrees or theta is equal to 120 degrees. Fantastic. Nice work, folks. You just solved your first trig equation. Now, if you felt comfortable with that, jump in to 1b. We're performing all of the same steps, actually just one extra step to get us going at first. But you should be able to handle it. Now, if you're not, that's okay. I'll go through it in detail here. I won't do that for every single question on here, but I think it will be beneficial for you folks. So we'll start off. Step 1, rearrange so that our trig ratio is isolated. Is it isolated here? No, it's not. What's our trig ratio? The cosine of theta. So it's like we're pretending, if you'd like, we could pretend that cosine of theta is an x. So we have 2x plus 4 equals 5. And I need to isolate for that x. So I'm working with 2x is equal to 5 minus 4. And that means that 2x is equal to 1. And that means x is equal to 1 over 2. Good, except the cosine of theta isn't necessarily x. So that's what our solution would look like if it were x, but it's not. But we deal with this as one big piece. So I go through the same steps. 2 times the cosine of theta is equal to 5 minus 4, where I've subtracted 4 from either side. That equals 1 on my right side. All right, so that means that if I divide both sides by 2, the cosine of theta is equal to 1 over 2. I'm hoping you see the similarities. Now, if the cosine of theta is equal to 1 over 2, we want to follow all of the same strategies that we followed in example 1b. We want to next draw the special triangle with the required ratio. So I need to draw a special triangle that has 1 and 2 as its side lengths. And what kind of side lengths? Well, I know I'm working with my cosine of theta, and I know that the cosine, and really it's going to be alpha that we're finding, right? The cosine of alpha is going to be equal to my adjacent side divided by my hypotenuse. So that means I need a hypotenuse of 2. Well, actually, that's just like the special triangle I drew last time. So let's sketch it out again. Remember, we need to include it in every single problem where we're using this to help us come to our solutions. Fantastic. So I need, first of all, that's step 2 done. Next, I need to find my related acute angle. Remember, this is the related acute angle we're finding in here, not not theta from our special triangle. So I know I'm working with an adjacent side of 1, so I need the angle adjacent to 1. That's 60 degrees. My hypotenuse is 2. Good, it passes the check. We're going along the right path. So if this is the case, that tells me that my theta is equal to 60 degrees. Good, and if my theta is equal to 60 degrees, I can use that along with my cast rule. Let's bring up our cast rule, CAST. What kind of a ratio am I working with this time? The cosine ratio. So the cosine ratio is positive in quadrant 4, it's positive in quadrant 1. It's negative in quadrant 2, and it's negative in quadrant 3. So that means I'm definitely not working in quadrant 2 or quadrant 3 because, and this is the key here, because this ratio is positive. If the ratio was negative, then we would only be working in these 2 quadrants. Good, so we're getting there. Awesome. Now, what that means is my terminal arm either lies in quadrant 1 or my terminal arm lies in quadrant 4. Either way, my related acute angle is measured against the positive x-axis. All right, so that means let's come up with equations for theta now that I know where I'm working and with my related acute angles. Okay, so here, first of all, in quadrant 1, I know that my theta 1, we'll call it, is equal to my related acute angle. Good, my related acute angle is 60 degrees. That means theta 1 is equal to 60 degrees. Good, we're coming to similar conclusions, to similar solutions as we did before. Now, this time, though, my theta 2 falls in quadrant 4. So theta 2 is going to be equal to 360 degrees minus alpha. Okay, so I can rearrange this. Sorry, I don't even need to rearrange it. I just substitute in 360 degrees minus 60 degrees. And I know that I'm working with a 300-degree angle for theta 2. And yes, I'm running out of space. That's okay. We can squeeze it in over here. Therefore, theta is equal to 60 degrees or 300 degrees. Fantastic work, folks. Now, I'll ask you folks to solve part C on your own. I'll encourage you pause the video, try out your solution, and then unpause to check to see how you did. I'm going to go through at least until the cast rule, to where I'm interpreting the cast rule here. So I'll say pause the video, get to your cast rule, interpret your cast rule, and then check to see how you did. And actually, to start us off here, if you weren't sure where to start, we need to work with a primary ratio if we're going to be using a special triangle. And so in exchanging this, transferring interpreting our work into a primary trig ratio and isolating that very well might help. Good, so we should be able to remember if we're working with our special triangles, then our side lengths can only be positive. So as much as this ratio is negative, at this point we only care about the positive aspect of it to find our related acute angle. Then we're going to use this negative for our cast rule. So I know I'm working with CAST. I know that in quadrant 1, my tan ratio is positive. In quadrant 3, my tangent ratio is positive. That means it's negative in the other 2 quadrants. And this is the key here. Yes, I know it's negative in the other two quadrants, but my tangent ratio that I'm working with is negative. So that means that my only quadrants in which I could be working are quadrants 2 and 4. Good, so now that I know I'm working in quadrants 2 and 4, I can sketch in my related acute angles right here, and then I can come up with and interpret at my solution. Try it out on your own. Good, so we should find that theta is equal to 150 degrees or 330 degrees. Note that here, neither of these angles theta are equal to our angle alpha. So we'll just need to keep that in mind. Yes, it was we had alpha equal to one of our theta options in A and B, but that's only because our ratios were positive in A and B. Fantastic. So you should be able to handle something like example 2 on your own. I am going to try and keep this this video lesson to a shorter amount. So if you are, let me see. So I'll encourage you pause the video, try it out on your own, and then come back and see how you did. And you know what? I realize here, I'm hoping you'll jump forward. I'm realizing that a part of the problem was missing. So let's get that into place. We should be working with the sine of theta is equal to negative 2 over 5. That will be included on yours. Good. So if the sine of theta is equal to negative 2 over 5, I know that I'm working with a sine ratio. And a sine ratio, according to my cast rule, a sine ratio is positive in quadrant 1. It's positive in quadrant 2. It's negative in quadrant 3, negative in quadrant 4. So this particular sine ratio is negative. And if this particular sine ratio is negative, that means that I will have to be working in quadrants 3 or quadrants 4. Fantastic. Now, this time we're not able to use a special triangle in order to determine our related acute angle, but we can determine our related acute angle by working with the positive ratio. So that means the sine of my alpha is going to be equal to 2 over 5. Good, and that means my inverse sine, I can take the inverse sine of both sides there. Let's do that nice and easy. There we are. This is how we isolate for an angle. We know that. The inverse sine, you've been doing this since grade 9. That means we're working with an alpha is equal to the inverse sine of 2 over 5. You can throw that into your calculator and find that alpha is equal to 23.6 degrees. So you should be able to, and the completed version will be uploaded to the classroom, you should be able to use that information for alpha to determine your two solutions, theta 1 and theta 2. So try it out on your own. We're going to jump in a little bit more. We'll just get to example 3, and then we'll have to call it quits for the lesson here. So example 3, this time we're going to be using a unit circle to justify our solutions. So we're looking for where the cosine of theta is equal to 0. Now, why do I need to use a unit circle for these solutions? Well, because I don't have any side lengths of right angle triangles with side length 0. But I do have, if you remember, I do have a unit circle. And on my unit circle, sometimes my cosine of theta, which is, we know, is equal to my x coordinate. My cosine of theta and sine of theta, that's equal to my x, y. So if that's the case, if I'm looking for the cosine of theta equal to 0, what I'm really looking for is where x equals 0. So where on my unit circle does x equal 0? Well, I know it equals 0 if my theta is, if my theta is equal to 90 degrees, or if my theta is equal to 270 degrees. So it's that easy. If you're justifying your work here, you need to sketch a unit circle, and then you just find those two angles. Theta 1 is equal to 90 degrees. Theta 2 is equal to 270 degrees. It's that easy. We can just throw a therefore statement right beside it. Fantastic. All right, so try it out for the sine of theta equal -1. Maybe pause the video, try it out, and if you're not sure, just keep going along with us. Okay, if the sine of theta is equal to -1, that means that my y-coordinate, which is equal to the sine of theta, that means my y-coordinate is equal to -1. Where is my y-coordinate equal to -1? Well, if I look over here, my y-coordinate equals -1 here and only here. So I'm working with, again, 270 degrees. So I use that logic to say, okay, theta is equal to 270 degrees. And you're seeing here, we're working with the same interval this whole time. Theta is in between 0 and 360 degrees. I'm using this logic, but sometimes we'll find there is only one solution. In fact, sometimes we'll find 3 solutions. Sometimes we'll find as few as no solutions. We'll have to see as we get there, and we'll need to justify our work the whole way. All right, lastly, we're working with the tangent of theta is equal to 0. Well, remember, the tangent of theta is equal to y divided by x. Okay, so if y divided by x is equal to 0, that means y is equal to 0 and x is not equal to 0 because we're not able to divide by 0. So I'm looking for somewhere on here where y is equal to 0. I'm working with at 0 degrees right in here and at 180 degrees way over here. And you might say, fantastic, we found all the solutions. I know that theta 1 is equal to 0 degrees. I know that theta 2 is equal to 180 degrees. But remember, the interval over which we're working here is where theta is in between or equal to 0 degrees and 360 degrees, which means that right here, I know it would share the same terminal arm, but 0 or 360 degrees fall into this interval, so we need to include both in our solutions. This is how we can find 3 solutions: 0 degrees, 180 degrees, 360 degrees. Fantastic. At this point, folks, you should be able to work your way through the rest of the practice problems. Particularly, practice 4B is a little bit challenging, but that's okay. If you're feeling good about it, you can do it. And if you're not feeling good about it, then head into the practice work and return to this after. And if you're looking for one more challenge problem here, folks, I can give you 3 times the cosine of theta plus 3 is equal to 2 times 1 minus the cosine squared of theta. And if you've never seen something like that before, don't worry about it. We'll get to this in our warm-up problem tomorrow. Nice work, folks. You know what to do.